Today we're diving into DeepSeek V3, a revolutionary language model designed to push the boundaries of open source innovation. With a jaw-dropping 671 billion parameters, this powerhouse blends efficiency and creativity, from multi-token predictions to an ultra-economical training process. Imagine training a behemoth like this with stability and precision, all while tackling benchmarks that rival top closed-source models. So, buckle up as we explore how DeepSeek redefines what's possible in language modeling.
Hey there! Let's start with an overview of DeepSeek V3. It's introduced as a mixture of experts model with a staggering 671 billion parameters, though only 37 billion are active when processing each token. This design choice helps keep inference efficient and training costs lower. The model uses multi-head latent attention and a carefully refined architecture from DeepSeek V2. One standout point is that it avoids the usual auxiliary loss for balancing the load among experts. Instead, it leans on a multi-token prediction objective for better accuracy. It's trained on a massive 14.8 trillion tokens, then goes through fine-tuning and reinforcement learning. All this allows it to excel at a broad range of tasks as parks. Despite its size, it only needs 2.788 million GPU hours to train. Quite practical compared to other similar models. According to the paper, it beats many open-source models and can even rival top proprietary systems. Check out the figure on this page. It shows a comparison of DeepSeek V3 and its competitors across 6 benchmarks, like math reasoning, coding accuracy, and general knowledge. DeepSeek V3 consistently ranks higher, especially on tough datasets such as Math 500, where it scores above 90% accuracy. Other models hit around 50% to 80%. It also leads on AIME 2024, showing strong reasoning skills. For Codeforces and SWE Bench Verified, the margin shrinks but still favors DeepSeek V3. The chart highlights not only the model's computational efficiency, but also its adaptability to various complex tasks. It's an interesting visual because it pinpoints the model's strengths and where there's room for improvement, especially in coding tasks. Moving on, this page talks about how open-source LLMs like DeepSeek, Llama, and Qwen have been catching up with proprietary systems, nudging us closer to general AI. DeepSeek V3 is a major stride in that direction. Even though its parameter count is 671 billion, only 37 billion are active per token, keeping it both powerful and efficient. It builds on prior inventions like multi-head latent attention and introduces new ideas such as auxiliary loss-free load balancing. This helps performance without extra overhead. There's also a multi-token prediction objective, making it flexible on benchmarks. For efficient training, it uses mixed precision methods, so it doesn't lose precision, but still cuts down on computational load. Here, the paper dives deeper into training efficiency for large-scale models. One key method is FP8 mixed precision, which boosts training speed and reduces memory. You'll also see the dual-pipe algorithm for optimizing pipeline parallelism, trimming down communication delays while training. The design allows the model to scale smoothly across nodes, even with fine-grained expert distribution. Plus, advanced hardware like NVLink helps reduce overhead. They don't rely on expensive tensor parallelism. Over 14.8 trillion tokens went into training, and the model maintained stable performance without big loss spikes. Text length was pushed first to 32,000 tokens, then to 128,000, so it can handle much longer inputs. After that, supervised fine-tuning and reinforcement learning refine the model to match human preferences without sacrificing accuracy or efficiency. Looking at Table 1 here, you'll find a breakdown of DeepSeek V3's training costs: pre-training, context extension, and post-training. Altogether, it took 2.788 million GPU hours on H800 GPUs, about $5.576 million. Pre-training alone used 2.664 million GPU hours, showing just how big a job it was. Despite that, the team managed to optimize the process with smart algorithms and hardware choices. The results were validated across multiple benchmarks, notably shining in math and coding tasks. It often beats other open-source models and even competes with GPT-4. So DeepSeek V3 strikes a unique balance of high efficiency and strong results, proving that advanced AI can be both potent and cost-friendly. This part of the paper splits DeepSeek V3's contributions into three key areas: architecture, pre-training, and post-training. Under architecture, the model introduces a way to balance computational loads without extra penalties. No more auxiliary losses. It also features a multi-token prediction goal that speeds up both training and inference. During pre-training, the model's large-scale precision framework is tested, nearly eliminating communication lags and curbing resource costs. The main pre-training phase only used 2.664 million GPU hours while creating a leading open-source model. Afterward, in post-training, they built on reasoning found in earlier models to fine-tune DeepSeek V3. This final polish boosts accuracy yet remains efficient. Now let's explore how DeepSeek V3 performs on a wide range of tasks: knowledge, coding, and reasoning. For educational tasks, it leads among open-source models on MMLU and GPQA, coming close to GPT-4 levels in some areas. It also does extremely well on Chinese factual tasks, outrunning its closest rivals there. On technical benchmarks, it reaches state-of-the-art results in math and reasoning, even surpassing previews like MA-500. In coding, it lands top marks in competitions like LiveCodeBench, confirming its robust engineering skills. Overall, DeepSeek V3 blends flexibility with specialized prowess in technical and factual reasoning, shrinking the gap between open-source and closed-source AI models. This next section digs into how DeepSeek V3 enhances the transformer blueprint with fresh techniques to boost efficiency and accuracy. It uses multi-head latent attention and a next-level mixture of experts approach, building on DeepSeek V2's success. These methods cut inference and training costs. A major new feature is the auxiliary loss-free load balancing strategy. It avoids the usual inefficiencies tied to unbalanced experts. Another is the multi-token prediction objective, which supercharges the model's ability to predict sequences and do well on benchmarks. Though grounded in DeepSeek V2, DeepSeek V3 pushes the boundaries further, delivering stability and lower costs. Here, we're introduced to DeepSeek V3's architecture in more detail, focusing on mixture of experts and multi-head latent attention. If you look at the diagram, you'll see a transformer core with specialized routing that boosts efficiency. It shows how hidden states flow through feed-forward layers and normalization. The DeepSeek MOE architecture assigns tokens to experts on the fly using a router that picks the best experts while cutting out duplicates. Meanwhile, multi-head latent attention uses caching and refined representations to handle complex queries effectively. Together, these techniques trim computation and pump up accuracy, especially for massive tasks. Now we shift focus to the multi-head latent attention (MLA) mechanism. MLA condenses the key and value parts of attention through low-rank approximations. This helps the model grab vital info during inference without storing heaps of data. It also uses rotation-based encoding to project hidden states smartly into keys and values. The payoff is big. Less computation and memory usage, which is critical as models scale for huge datasets or extremely long sequences. MLA aims to keep everything streamlined while holding on to accuracy and reducing inference time. Diving deeper into MLA, we see how it tackles attention queries and memory during training. By shrinking the key and value vectors into smaller representations, memory demands for caching go way down, especially in inference mode. Rotational position encodings align attention across sequences, boosting overall performance. This compression applies to queries as well, cutting memory use further. In the end, the attention mechanism pulls together these compressed elements to create the final output. The result? Faster, lighter attention that still keeps performance competitive. This part introduces the DeepSeek MOE architecture, which rethinks feed-forward networks. It separates experts into two sets, shared and routed. Shared experts tackle common tasks, while routed experts focus on certain tokens using a probabilistic score. A gating system determines which routed experts light up for each token, ensuring resources are used efficiently. By splitting expert roles, DeepSeek V3 avoids piling too much work on one piece of the network, making it more scalable. A gating mechanism calculates a score for each token and then picks the most relevant routed experts, boosting efficiency and balancing the load. Here, we learn about a major improvement in DeepSeek MOE, auxiliary loss-free load balancing. Mixture of experts models often suffer from routing collapse, where one or a few experts get overloaded. Normally, an auxiliary loss is used to fix that, but it can hurt performance. DeepSeek V3 bypasses that trade-off by adding a bias terms. This bias adjusts how tokens are routed so that top experts get chosen without overwhelming any single one. During training, the system tracks this distribution to keep workloads balanced. The outcome? A finely tuned routing strategy minus the drawbacks of earlier methods. To keep workloads evenly spread out, DeepSeek V3 pairs its auxiliary loss-free method with a sequence-wise strategy. This extra layer keeps any single sequence from leaning too heavily on one expert. The secret is the balance factor, which tweaks the contribution of each expert at the sequence level. Because of this, the model avoids performance hits due to uneven loads, even under tough workloads. It's a straightforward but effective way to make sure everything runs smoothly, showing off the model's robust, scalable design. Now let's look at the multi-token prediction framework. In the diagram here, you'll see how DeepSeek V3 predicts the next token, or sometimes several tokens across different layers. Each module works on its own slice of the timeline, building a causal chain of predictions. There's also a node-limited routing component. That means tokens only travel to a set number of nodes based on their affinity scores, limiting overhead but still capturing enough information. All these features together give DeepSeek V3 a boost in both efficiency and accuracy. Within DeepSeek V3, no tokens get dropped during training or inference. Stability is maintained through effective load balancing. Next, the multi-token prediction (MTP) framework expands the model's view by predicting multiple future tokens for each position, improving efficiency and giving the model more look-ahead during representation planning. MTP layers are arranged in sequence. Each layer tackles extra token predictions while staying consistent with the causal flow. For each prediction, the current token's representation is combined with the embeddings of future tokens, making sure context stays cohesive at every step. This page continues with MTP, describing how each MTP module shares the same embedding layer and output head as the main model. A linear projection plus special transformations are used to estimate tokens further in the sequence, while preserving the causal order. This encourages speculative decoding, letting predictions about future tokens refine current representations. Probability distributions are generated via the shared output head. It applies transformations that map the compressed representations into final token probabilities. This design supports efficient training and creates a richer sense of context. Here, we learn that MTP can predict multiple future tokens at once, which boosts training efficiency. The predicted probabilities go through a loss function, comparing them with real tokens. During inference, these extra MTP modules aren't needed, so the main model can run on its own. The framework also supports speculative decoding, speeding up text generation. Next, the paper shifts to the hardware setup. DeepSeek V3 is trained on 2048 NVIDIA H800 GPUs, grouped into nodes connected by NVLink and NVSwitch, plus InfiniBand for cross-node data exchange. It's all about pushing throughput in a distributed training environment. Now we look at the HAI LLM platform used to train DeepSeek V3. It's designed to optimize data flow and pipeline management. The dual-pipe algorithm stands out because it overlaps compute and data transfer, removing pipeline stalls. Combined with InfiniBand and NVLink, data moves quickly between GPUs. Carefully managed memory keeps performance high. The figure here illustrates parallel forward and backward passes for greater efficiency. Dual pipe is a pipeline parallelism method that overlaps forward and backward passes with data exchanges. It partitions each step like attention and dispatch. So computation and communication run simultaneously, lowering overhead. This near elimination of all-to-all delays speeds up training and helps balance both computation and communication as the model scales. Figure 5 shows how dual pipe schedules 8 ranks and 20 microbatches to minimize idle time. Table 2 compares it with other methods, such as 1F1B and ZB1P, confirming that dual pipe reduces pipeline bubbles and improves memory use. Even with light communication, it optimizes resource use and throughput, offering a neat step forward in pipeline parallelism. DeepSeek V3 also optimizes GPU communication using NVLink for intranode speed and InfiniBand across nodes. Only specific GPUs handle communication to prevent congestion, directing tokens where they're needed. This ensures quick data movement, avoids bottlenecks, and keeps the system running smoothly, even when many GPUs are involved. DeepSeek V3 splits GPU resources into channels for simultaneous sending and receiving, letting communication overlap with computation. Warp specialization helps distribute tasks evenly, avoiding jams. It also recomputes some layers, like normalization, during backprop to save memory. This way, it boosts performance and keeps memory demands in check. Additional memory optimizations include using EMA to track parameters on the CPU, saving overhead. Embedding and output layers are shared to reduce duplication. The model also adopts FP8 precision, blending speed with accuracy. Managing outliers in activations and weights helps keep training stable, despite using lower precision formats. The FP8 mixed precision approach speeds up training while addressing low precision concerns. Tile-wise quantization groups computations into small blocks, maintaining error control. Activations are cached in slightly higher precision, and optimizer states are efficiently stored. Tests show it sustains high accuracy across large-scale training with minimal errors. In this setup, most operations use FP8 for faster compute and smaller memory footprints. However, critical pieces like embeddings and output layers stay in higher precision for stability. Some weights and optimizer states also remain at higher precision, creating a balanced mix of speed and reliability. Next, the paper describes fine-grained quantization to handle outliers. It works on smaller segments, such as 128 elements, to reduce errors when dealing with extreme values. CUDA cores at these intervals keep precision tight, especially in FP8. Combined with distributed training, this method stays both memory-friendly and robust. Outliers in FP8 training can cause big precision problems. By grouping and scaling data at small levels, we avoid serious errors. Adding scaling factors in specific steps further refines accuracy. Higher precision accumulation also helps stability. Together, these techniques manage large computations without losing precision in low precision environments. FP8's limited range can cause underflow in big workloads. The paper's solution is to switch to higher precision during accumulation, so computations remain accurate while the main multiplications stay in lower precision. This approach supports massive models without major precision losses. The text then outlines more FP8 refinements. Per-group scaling mitigates large matrix operations, and E4M3 quantization balances exponent and mantissa bits. Delayed quantization tracks maximum values over time to adapt scale. These strategies safeguard stability, letting the model leverage FP8 speeds. To save memory and control communication overhead, optimizer states are often stored in lower precision, while essential parameters keep higher precision. Some activations are also cached in low precision after attention, cutting memory load. This blend of strategies maintains accuracy while reducing resource demands. The paper then covers memory efficiency in deployment. It quantizes key activations but keeps vital elements precise. Communication-heavy operations are streamlined for speed. Pre-filling and decoding are split into separate stages on H800 GPUs, each optimized for its own task, ensuring fast and reliable service. For the pre-filling stage, DeepSeek V3 uses 4 nodes with 32 GPUs, layering tensor, sequence, and data parallelism to reduce communication. Redundant experts help distribute tokens evenly, preventing GPU bottlenecks. Microbatches are processed in parallel, overlapping attention with expert tasks for higher throughput. In decoding, each token can tap multiple experts, with some always active. The minimum setup is 40 nodes with 320 GPUs, using tensor and sequence parallelism. Each GPU has one expert, plus redundancies to balance load. Periodic routing adjustments keep performance solid, minimizing inference cost. Decoding speed gets a boost by overlapping tasks between microbatches. While one batch handles attention, another tackles expert computations. Smaller decoding microbatches need fewer resources. Future hardware might benefit from dedicated communication units, since current multiprocessors also handle data transfers, raising costs. The paper also suggests hardware upgrades, offloading data forwarding, reduction, and memory tasks to specialized coprocessors, freeing main units for computation. It recommends bigger accumulation bit width in tensor cores, as 14 bits can be limiting. Overall, better resource allocation and higher precision could greatly accelerate large-scale workloads. They continue discussing precision improvements. Moving from 14-bit to 34-bit accumulation in tensor cores would increase accuracy. Additionally, fine-grained quantization should be integrated directly into tensor cores to avoid extra data movement. Online quantization could let the system adapt on the fly, boosting speed and reliability. Finally, the authors call for more efficient GPU operations via unified memory reads and quantization, having data transfers. Directly reading matrices in transposed form would also save time. These tweaks would streamline training and inference, cutting overhead and improving speed for large models. Now we turn to how DeepSeek V3 is pre-trained. The team improved the data corpus from DeepSeek V2 by adding more balanced math and programming texts and broadening multilingual coverage. They also polished the data pipeline to reduce duplicates, ending up with 14.8 trillion tokens total. A clever technique, fill-in middle, or FIM, helps the model predict missing parts of a sequence without messing up next token predictions. This is done with a prefix-suffix middle approach. Meanwhile, the tokenizer has a vocabulary of 128,000 tokens, making it more efficient for multilingual data. Here, you'll find the hyperparameters that power DeepSeek V3. It has 61 transformer layers, each with a hidden size of 7,168, plus 128 attention heads. Each MOE layer has a shared expert and 256 routed experts for split tasks. Out of those 256, only 8 are lit up for each token, preventing communication overload. Altogether, that forms the 671 billion total parameters, with 37 billion actually used per token. The paper also mentions the AtomW optimizer for stable, efficient updates. During pre-training, the sequence length can go up to 4,000 tokens, allowing the model to handle quite complex inputs. This section focuses on the training schedule. They warm up the learning rate gradually, hold it steady, then slowly decay it. Gradient clipping is in place to keep updates stable. Batch sizes also ramp up in the early phases for computational efficiency. Tokens route across multiple nodes, but with limits to reduce any slowdowns. And they apply loss balancing so sequences don't become lopsided. All these steps, plus pipeline parallelism, help DeepSeek V3 handle vast amounts of data while maintaining top performance. Here we see how the model extends its context abilities. After the main training, they do context extension in 2 phases, from 4,000 tokens to 32,000, then up to 128,000. They keep the same hyperparameters for consistency. They just stretch out the sequence length and adjust batch sizes to handle the extra work. This is crucial for tasks that rely on large contexts, letting DeepSeek V3 handle long, detailed inputs without losing track of the bigger picture. Evaluation time. DeepSeek V3 is tested on a range of tasks. The core dataset is multilingual, mostly English and Chinese, but the model is also checked on multiple choice questions, language reasoning, question answering, and reading comprehension. Some tasks focus on zero external resources, others stress robust reasoning. And there's a big focus on non-English tasks too. These checks reveal how well the model generalizes to new languages and different complexities, gauging its overall adaptability. In this section, we get more detail on the variety of benchmarks, including reference disambiguation, language modeling, Chinese comprehension, math, and coding. For instance, CCPM tests the model on cultural context, while GSM-8K looks at math problems. Human Evil and LiveCodeBench examine coding skills. A GI eval hits both English and Chinese exams. They also use perplexity and generation-based metrics for comparisons. Bits per byte is mentioned for language model evaluations. This well-rounded set of metrics ensures the model is measured thoroughly. Now let's compare DeepSeek V3 with dense models like QN 2.5 and LLA MA 3.1. Benchmarks include language tasks such as MMLU and RACE, math tasks like GSM-8K and MA-TAF, and coding tasks like Human Evil and MBPP. DeepSeek V3 consistently shows improvements, especially in problem-solving and code generation. Thanks to its mixture of experts approach, it uses parameters more efficiently, so it achieves high accuracy on complex tasks without blowing up the computational budget. Here, the paper zooms in on how DeepSeek V3's base model compares to DeepSeek V2, QN 2.5, and LLAMA 3.1. Across math, language, and coding benchmarks, DeepSeek V3 comes out on top. It even beats them on tough sets like CMath and Human Evil. These gains are credited to improved parameter handling and architecture updates. Though test conditions may vary slightly, the message is clear. DeepSeek V3 offers strong precision and computational efficiency across multiple tasks, solidifying its lead in the open-source sphere. We keep going with these comparisons. DeepSeek V3 stands out versus DeepSeek V2, QN 2.5, and LLAMA 3.1 in English, multilingual, math, and coding benchmarks. Interestingly, it achieves these strides without needing an enormous number of activated parameters. For multilingual and Chinese-specific tests, it usually outdoes QN 2.5. Its training efficiency is also highlighted. It delivers superior performance with fewer computational resources. That makes it a compelling option for large-scale AI needs. Now let's talk about the multi-token prediction (MTP) strategy, tested via ablation studies on two different model scales. A 15.7B parameter model trained on 1.33T tokens, and a 228.7B model on 540B tokens. MTP was added as an extra layer, then removed during inference so there's no extra cost at runtime. The results? Consistent performance boosts across almost every benchmark. So MTP proves its worth by enhancing training outcomes without slowing down inference. This page covers the auxiliary loss-free balancing strategy, also tested in ablation form. Again, two scales are tested, 15.7B parameters and 228.7B parameters. Compared to standard auxiliary loss-based methods, the auxiliary loss-free version did better on many benchmarks. It balances the workload across experts without extra compute. Essentially, it shows that ditching the auxiliary loss can increase efficiency and maintain strong results. Here, batch-wise versus sequence-wise load balancing is discussed. Batch-wise is praised for its flexibility. It doesn't force balancing at the sequence level, giving experts more room to specialize. Large model experiments show that batch-wise balancing performs similarly to auxiliary loss-free balancing, sometimes with even lower validation losses. It suggests that focusing on load balance across the entire batch, not each sequence, yields better specialization with no drop in performance. Moving on, we see a domain-based load analysis on the pile test set. Turns out, auxiliary loss-free models let experts specialize more effectively in domains like Wikipedia, GitHub, and math. The paper shows heat maps of how tokens are distributed across experts, revealing that the no-aux loss approach naturally leads to better domain specialization. This helps improve performance without forcing a strict balancing act, making the training more adaptive to real data. This section has two topics: batch-wise auxiliary loss and supervised fine-tuning for reasoning datasets. Batch-wise auxiliary loss balances loads across sequences and microbatches, smoothing out domain-driven fluctuations. Then there's fine-tuning on curated data, with 1.5 million examples from multiple domains. For reasoning tasks, math, logic puzzles, some data came from an older version of the model. It's usually accurate, but can be verbose. The team aims to combine that accuracy with concise reasoning data to produce higher quality final outputs. To craft an expert model for math or general reasoning, they do both supervised fine-tuning and reinforcement learning. Two sample types are generated, one with just a problem and solution, another with a system prompt that encourages deeper reasoning. High-temperature sampling also pulls from older model patterns. Over time, the model refines itself, merging new knowledge with established frameworks. After RL, rejection sampling picks out top-quality data that's both clear and correct. For non-reasoning data, human checks ensure correctness and precision. They use two reward systems, rule-based and model-based. Rule-based rewards come into play for tasks with definite correctness criteria, like math solutions. A compiler or set of rules can validate the output. For open-ended questions, a model-based reward looks at how closely responses match an expected style or solution. By mixing both, they cover tasks that require strict accuracy and those that need a bit more creativity or interpretation. To boost reliability and reduce risks, the reward model uses data that captures final rewards and the steps in between, so you see exactly how the evaluation is done. Group Relative Policy Optimization, GRPO, steps in for the usual critic model. Instead of just one critic, multiple outputs are scored and compared, leading to more stable optimization. It balances exploring new ideas while staying aligned with known good behaviors, making training more efficient and dependable. Now for the updated evaluation benchmarks. Beyond the base model checks, they include tasks like IF eval, frames, and LongBench V2. These tests cover general QA, advanced math, and more. DeepSeek V3 Chat is compared with strong open-source models like DeepSeek V2, QN 2.5, and LLaMA 3.1, and closed-source ones through their APIs. This thorough approach means we get a well-rounded sense of how DeepSeek V3 measures up across various tasks. On this page, they run DeepSeek V3 through standard datasets like MMLU and DROP, with zero-shot prompts for fairness. For coding and math tasks, they check multiple languages and chain of thought, co- or non-code methods. Codeforces is tested by seeing what percentage of participants the model beats, an interesting measure. Math tasks use specific temperatures for sampling and average out multiple runs to ensure reliability. The table here shows DeepSeek V3 often pulls ahead of rivals on these demanding benchmarks, highlighting its power and versatility. We stay on performance comparisons with other top models. DeepSeek V3 shines again in code, math, and Chinese tasks. It sets a new bar among open-source models, even nibbling at the heels of some closed-source heavyweights. That includes doing extremely well on math tasks and Chinese benchmarks, bridging some of the performance gap. This cements its place as a serious contender in open source, going toe-to-toe with major proprietary models. Here we see that DeepSeek V3 is basically the leading open-source model, challenging GPT-4 and Claude on MMLU, MMLU Pro, MMLU Redux, and more. For long context tasks like DROP and LongBench, it can handle text that's over 100,000 tokens long, which is pretty extensive. In a three-shot setting on DROP, it puts up strong numbers. On frames, it handles queries requiring over 100K tokens, surpassing other models. So it's not just good at short tasks, it's also robust for extended contexts and complex reasoning. Next, they evaluate coding and math tasks. DeepSeek V3 impresses on Human EvilMul and LiveCodeBench, outperforming other open-source models but still trailing certain closed-source solutions. But for math, it does even better. It sets new records on benchmarks like AIME, Math 500, and CNMO 2024, surpassing its closest challenger by 10%. This is thanks to a strong distillation approach that helps it handle advanced problem-solving. All in all, it's a top performer for tasks that aren't simply about scale. Now we move into open-ended conversation benchmarks in both English and Chinese. Models are judged with length-controlled win rates. DeepSeek V3 comes out on top, beating GPT-4 and Claude in English tasks. For Chinese data, it scores high on factual tasks like Chinese Simple QA, even beating QN 2.5 to 72B, despite fewer training tokens. Both models do well in reasoning and educational tasks, confirming that DeepSeek V3 is well-tuned for Chinese as well. DeepSeek V3 also performs superbly on open-ended generation tasks, reaching over 85% on the Arena Hard benchmark. No other open-source model has done that yet. On Alpaca Eval 2.0, it leads by around 20% compared to older open-source models. It also functions as a generative reward model, using voting-based feedback to enhance how it judges open-ended questions. This adaptability makes it useful for more than just standard QA. It can handle a wide range of generative scenarios. Here the paper shifts to reward bench results. DeepSeek V3 is almost on par with Claude 3.5 and GPT-4 variants in conversation, safety, and reasoning. The tables show that distillation methods improve math and coding outcomes. For example, distilling from DeepSeek R1 pushes up success rates on LiveCodeBench code and Math 500 and lengthens outputs. Overall, the model does well in critical thinking tasks and safety, proving that the right distillation steps can refine its skill set. In more reward bench details, we see that DeepSeek V3 not only keeps pace with top-tier models, but also shows consistent gains when applying distillation. Success rates go up across coding and math, reinforcing the idea that refining your training strategy can yield clear improvements. LiveCodeBench-COT and MATH-500 are prime examples. In short, these results reveal how well the model can be shaped for alignment and performance through iterative distillation processes. Next, we learn about the role of constitutional AI in shaping alignment and rewards. The model uses its own feedback for evaluation, which helps in more subjective tasks. Additional constitutional inputs are integrated, ensuring that broader contexts are accounted for. On top of that, the multi-token prediction approach steps things up by predicting the next 2 tokens instead of 1, and with speculative decoding, it nearly doubles decoding speed. Acceptance rates for those token predictions stay high, showing it works reliably for a range of uses. Wrapping up the key points, DeepSeek V3 is a large model with 671 billion parameters that's designed for high performance at a reasonable cost. It introduces auxiliary loss-free load balancing and multi-token prediction to boost efficiency. FP8 precision further reduces training expenses, and the post-training steps keep building on the model's reasoning skills. It still has limits, like large deployment units, which might be tough for smaller setups, but it achieves fast generation, twice the speed of DeepSeek V2. By joining the open source community, it aims to keep advancing AI's capabilities and adaptability. Finally, the paper looks ahead at DeepSeek V3's future. The team wants to make training and inference even more efficient, potentially going for near-infinite context lengths. They'll keep examining the transformer design for bigger and deeper expansions, and plan to improve training data both in quality and diversity. Another goal is to grow the model's problem-solving depth, encouraging more complex reasoning. They also want to refine how they evaluate the model to avoid overfitting on-set benchmarks. All of these measures aim to deliver a model that reflects real-world performance more accurately, pushing AI boundaries further. And that wraps up our look into DeepSeek V3. With its ambitious plans for near-infinite contexts, more efficient training, and deeper reasoning, it's clear the journey is far from over. The research team has laid out a roadmap for pushing AI boundaries even further, so stay tuned to see where DeepSeek V3 goes next.